In this final lecture, we take a step back to view the entire panorama of number theory. Inspired by a tale of Thales, the pre-Socratic Greek philosopher and teacher of Pythagoras, we'll see number theory and mathematics more generally as the art of not only looking up into the entire sky of numbers, but also looking down to earth closely at the detail within the numerical terrain at our feet. We'll open with a panorama involving the continued fractions for almost all numbers. We'll then consider the growth rate of partial quotients within the context of quadratic irrational numbers and Liouville-type numbers, and highlight an attractive result of Paul Erdős and its recent generalizations. Standing back a bit further still, we'll take a final look at the entire mosaic of number theory that we created. In particular, we'll celebrate some of the synergistic moments in which seemingly unrelated ideas came together to tell a unified story of number. Finally, we'll close our course by looking beyond number theory and mathematics and highlight the underlying theme of creativity and originality that made our entire journey possible. Here, we'll explore this mindset and how it has a transformative effect, not just within the narrow, endless confines of number, but within the boundless possibilities of our own lives and imagination. Well, we've seen in the past few lectures that to truly understand the number theoretic structure of real numbers, we should consider their continued fraction expansions. Well, I want us to conclude our explorations into the theory of continued fractions by noting that continued fractions can be viewed as the digital DNA of real numbers. In particular, the numbers that make up the continued fraction expansion for a real number, say alpha, the so-called partial quotients, the A's that we saw, hold alpha's digital DNA. In other words, the partial quotients hold all the information about the personality of alpha. For example, truncating the continued fraction expansion produces the complete list of best rational approximations to that real number. The partial quotients can reveal features of the number alpha itself. For example, we've shown that the partial quotients of alpha form an endless list if and only if alpha is an irrational number. We've also seen that the partial quotients of alpha eventually become periodic and repeat endlessly if and only if alpha is a real quadratic irrational. Other numbers have other types of patterns in their continued fractions and through their partial quotients. The partial quotients, for example, for Euler's E, have the very easy to identify pattern of 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, and so forth. On the other hand, the partial quotients for pi exhibit no obvious pattern and appear to be, in some sense, chaotic. Suppose we were to pick a real number at random. Let's call this random real number alpha. Let's recall from lecture 20 that a real number selected at random will be transcendental with probability 100%. Thus, we are very confident that the continued fraction expansion for this random number alpha will not be periodic, because remember, periodic implies quadratic, which in turn implies algebraic, the opposite of transcendental. So, what values might we expect to see as alpha's partial quotients? Recall that the partial quotients are defined to be the integer part of the reciprocal of a previous fractional part. So, for example, if we have a fractional part at some point in our process of, let's say, 0.1179, then we'd consider its reciprocal, which would be 1 over 0.1179, which would equal 8.4817 and so forth. And then we would pull off the integer part 8 and then add 1 over the reciprocal of the fractional part, which would be 8 plus 1 over 0.4817, and so forth, which would equal 8 plus 1 over 2.0757, and so forth. And so then we pull off the 2 and then have another fractional part, and so on. That was the process we saw to generate a continued fraction. Well, let's now focus on the fractional parts in general and see what kind of partial quotients they give rise to. Well, since a fractional part of any number is always between 0 and 1, because it's just the fractional part, let's imagine selecting a random number between 0 and 1. If we consider its reciprocal, then the integer part of that reciprocal would be some integer, some natural number, and the question is, what would we expect to see for that integer part? Well, if our fractional part falls within the half interval from a half to 1, so here's 0 to 1, and if we look at just half of the interval from a half to 1, so if we pick something in this half, then it turns out that the integer part of the reciprocal of those numbers will always be 1. For example, consider the fractional part 0.6. That's 6/10. Its reciprocal, therefore, would be 10/6, which equals 5/3, which is 1.6666 forever. Notice the integer part is 1, as we claimed. So we'd guess that if these fractional parts were being selected at random from the interval from 0 to 1, then about half of them, or about 50%, would have reciprocals with integer parts equal to 1. Because if we have the entire interval, we would expect, if we're picking at random, half of them to fall into this half, which would have integer parts equal to 1. If our fractional part falls within the tiny subinterval between 1/3 and a half, so that little interval right here, then it turns out that the integer part of the reciprocal will equal 2. For example, if we consider the decimal number 0.35, notice that 0.35 is indeed bigger than 1/3 but smaller than a half. So it's in that little narrow interval. Well, 0.35 is 35/100ths. Its reciprocal is 100 over 35, which is 2.85, and so forth. Notice the integer part is indeed 2. Well, the interval between 1/3 and a half has length equal to a half minus 1/3, which is a sixth, or 0.16666 forever. So we might guess that approximately 16.666% of the partial quotients should equal 2, because if we pick a number out at random from 0 to 1, then getting in that little interval of length 0.1666, you'd expect to happen around 16.6% of the time. In other words, we might guess that if we pick a random real number out and look at its partial quotients in its continued fraction expansion, about 50% of them would be 1s and about 17% would be 2s. Notice the precipitous drop. Well, this pattern, in fact, continues. With smaller and smaller likelihoods, we'd expect to see larger and larger integer parts. In other words, larger and larger partial quotients. Well, these informal observations can be made precise and are quantified in a result now known as the Gauss-Kuzmin distribution. It states that if we select a random real number and consider its continued fraction expansion, then within the partial quotients, we would expect to see every natural number appearing infinitely often. So all the natural numbers should appear in this continued fraction infinitely often if the number is random. And with the most popular partial quotient, the most popular number being 1, then followed by 2, then followed by 3 in popularity, and so on all the way down. More precisely, by the Gauss-Kuzmin distribution, we'd expect to see the partial quotient 1, the number 1, roughly 42% of the time, which notice is close to the 50% of the time that we just guessed, thinking about numbers between 0 and 1. And we'd expect to see the partial quotient 2 about 16.9% of the time. 16.9, that's almost exactly what we conjectured looking at our little heuristic. Approximately 9% of the time, we'd expect to see the partial quotient of 3, and so on. The percentages continue to drop as the numbers get larger. However, for each natural number, we'd expect to see that number as a partial quotient a positive percentage of the time. Even though the percentage might be extremely small, since it's positive and we have infinitely many partial quotients to select, just like rolling dice, we would expect to see every number come up and come up infinitely many times. Although we'll see the smaller numbers more frequently than the larger ones, but we would see them all in a random real number. In view of our previous observations and this Gauss-Kuzmin distribution, we'd expect to see a great many ones appearing in the continued fraction expansion for a random real number. And recall that we saw many ones appearing in the first few terms of the continued fraction expansion for pi. This observation is now a bit more meaningful in light of these new insights. However, for a random real number, we now see that the partial quotients grow without bound, while we still do not know if the partial quotients for the special number pi are bounded or unbounded. Very large partial quotients give rise to surprisingly close rational approximations with relatively small denominators. If the partial quotients of a real number alpha are bounded, in other words, they're all less than or equal to a fixed value, so they all come under a certain ceiling, then alpha is called a badly approximable number. This name follows because small partial quotients prevent the best rational approximations from getting too close to alpha too fast. Real quadratic irrational numbers are badly approximable. Now why? Well, because remember, there might be some junk at the beginning of the continued fraction expansion, but from some point on, it becomes periodic. Well, since it's periodic, there are only finitely many numbers that appear from this point onward. We can find its biggest one, look for the biggest one in this finite pre-period, and we see that all the partial quotients are bounded by that biggest. So in fact, these numbers are badly approximable. And the most badly approximable number, if you will, is of course the golden ratio, because those partial quotients are as small as possible. They're all ones. Now recall that the golden ratio is also considered the least irrational number. And all these ideas now fit together because recall that we proved way back that the rational numbers in some sense repel other rationals with small denominators in some sense. Well, let's recall that Liouville numbers are real numbers that have incredibly close rational approximations with relatively modest denominators. This property allowed Joseph Liouville to prove that such numbers are in fact transcendental. And we saw the first Liouville number, which were just made up of ones and zeros, in lecture 20. The fact that Liouville numbers have such excellent rational approximations implies that Liouville numbers have partial quotients that grow dramatically and without any bound. In some sense, they're the opposite of badly approximable numbers. They have amazing rational approximations with relatively modest denominators. It turns out that Liouville numbers have such amazing rational approximations that these numbers are extremely rare. If we pick a number at random, it's with probability 0% that we accidentally select a Liouville number, which is a little bit funny to think about because remember, Liouville himself showed that these Liouville numbers are transcendental, and we know that if we pick a number out at random with probability 100%, we would expect to see that number to be transcendental. But this is a very, very sparse sub-collection of transcendental numbers. So sparse that when we pick the number out at random, even though we think it will be transcendental, we think with probability 0, it will be one of these special Liouville numbers. They're very, very, very thin. Well, even though the Liouville numbers are extremely rare, in 1962, Paul Erdős gave a very clever argument showing that every real number can be written as the sum of two Liouville numbers. So even though they're very uncommon, every number can be expressed as the sum of two of them. And about 35 years later, in 1996, I was able to generalize Erdős's result and show that given any non-trivial function of two parameters or two variables, let's call it f of x and y, and any real number alpha, we can find two Liouville numbers x and y such that f of x and y equals alpha. If we let f of x and y equal x plus y, that simple function, then we have Erdős's original result in this very special case. But you can see the theorem applies to much more interesting functions rather than just the sum. These results show that even though Liouville numbers are extremely rare, they can be combined two at a time to generate all numbers. Well, as our course comes to a close, I invite us to take a moment to reflect back upon the entire number mosaic we've created through our journey. I'm reminded of an ancient tale about Thales of Miletus. Thales was a pre-Socratic philosopher and scholar from around 600 BCE. He's regarded as one of the first philosophers in the Greek tradition, and some even consider him as the father of science. In fact, he was one of Pythagoras' teachers, so you could see he'd certainly had influence on science and mathematics. Well, toward the end of his life, Thales dedicated himself to the study of astronomy. And there's a famous story about one particular night of study. As the tale goes, one evening Thales was staring up at the stars as he took a nighttime stroll. While gazing at the stars, he fell into a ditch. Well, his woman attendant, who witnessed his foolish fall, looked at this great scholar lying on the ground and asked, "How can you know what's happening in the heavens when you don't see what's at your feet?" Well, it's a wonderful lesson for us all. Here, we highlight some great moments from our journey together, both the amazing results now at our feet, as well as the heavenly panorama that allows us to appreciate all the surprising interconnections that made these results a reality. At the opening of the course, we pondered if there existed a power of two whose digits, the first few digits when read left to right, would coincide with our own Social Security numbers. More generally, we wondered, given any natural number A, if there existed a natural number B such that the leftmost digits of 2 raised to the B power agreed with the digits of A. Upon first inspection, this question appeared entirely out of reach. However, once we extended our reach into the world of irrational numbers, we discovered Kroneker's theorem. Kroneker's theorem told us that the fractional parts of multiples of irrational numbers are dense within the interval from 0 to 1. This fact, together with our proof that the log of 2 is irrational, is enough to prove that the powers of 2 can begin with any prefix we desire, even our Social Security number. Notice that to prove a theorem about natural numbers, we had to venture into the mysterious and formidable world of irrationality. We first encountered issues involving the chromatic scale from music in our discussion of geometric progressions, progressions of numbers whose ratios of consecutive terms are constant. In order to understand why the chromatic scale contains 12 notes, we required best rational approximations to an irrational number log base 2 of 3/2. Thus, to derive the length 12 in our 12-note chromatic scale, we required the continued fraction expansion of this auxiliary irrational number. So we answered a musical question involving geometric progressions and ratios using the theory of continued fractions, irrational numbers, and best rational approximates. Fermat's famous last theorem was the inspiration for Lamé's clever but incorrect proof that there are no natural number solutions to x to the n plus y to the n equals z to the n for any natural number n greater than 2. Lamé factored Fermat's equation and assumed that certain algebraic integers behaved like the ordinary integers. In particular, he assumed that they possessed the unique factorization property into primes that Euclid had established centuries before. Unfortunately, Lemay's particular algebraic numbers do not exhibit the unique factorization property, and so his proof fell flat. This failed attempt, however, inspired Kummer to discover ideals, packets of algebraic integers that do exhibit unique factorization into prime packets. This beautiful insight gave birth to algebraic number theory and hundreds of important new insights about the nature of the natural numbers. Prime number theory focuses on the structure of the fundamental multiplicative building blocks of the natural numbers. The primes, of course, you'll remember, are 2, 3, 5, 7, 11, 13, and so on. However, to understand their nuanced properties, as in the prime number theorem telling us how many primes we have up to any given point as we drift off to infinity, or the Riemann hypothesis, the famous open question that tries to refine the question involved within the prime number theorem. We are required, in order to study these primes and these questions, to journey into the foreign and complex world of imaginary numbers and logarithms. In order to understand integer or rational solutions to certain Diophantine equations, we discovered that their rich structure is revealed through the study of curves and their intersection with lines. Thus we see the powerful marriage between geometry and arithmetic, which gave birth to algebraic geometry. Well, we now see that the world of diverse ideas is in fact a connected whole. One theme we've seen again and again is that notions that at first appear to be disconnected and unrelated are, in fact, inextricably intertwined. As our understanding of nature and number deepens, objects that first appear different become connected. It is this deep interconnection that allows us to move the frontiers of discovery forward. This raises an interesting question. How do we move the boundaries of our own creativity and understanding forward? Mathematics in general, and number theory in particular, require us to create. Mathematicians are at once artists, generating new and imaginative ideas, and also explorers, trying to understand truth within our universe, both the concrete and abstract world around us. However, the mindset that allows us to move the frontiers of number theory forward also empowers us to move our own boundaries outward as well. We can be more creative and imaginative by deliberate intent, by embracing certain habits of thinking that we employed here throughout our number theory journey. Thus, I wanted to close our course with my top 10 list, if you will, of life lessons that have been constants throughout our creative journey through mathematics and can be constants throughout our entire lives. The first life lesson is just do it. The notion of taking an action, not being afraid to make a move, even if you're unsure where that move's going to lead you. Taking an action is the most important step to trying to make a discovery, especially in light of my second life lesson, which is make mistakes and fail, but never give up. We've seen time and time again how false starts and failed attempts have led us to new insights that allowed us to finally conquer the issue at hand. If we never make mistakes, then in fact we will never learn anything. If we want to genuinely create something new, we have to not walk along a paved path. For that paved path was paved by someone else before us and won't lead to any place that's been uncharted. Instead, we have to intellectually trailblaze and go through the jungle of ideas, bad ideas, good ideas. We'll hit brick walls, we'll get to dead ends. But every dead end, every brick wall allows us to understand the actual issue at hand and to make progress forward. My third life lesson that we've seen throughout our course together is to keep an open mind. The very notion of number, the fact that the Pythagoreans saw the natural numbers as God-given and ratios weren't even quite numbers and irrational numbers disturbed people, well, that's just a reality of how human beings work. When we come to any issue, mathematical or especially otherwise, we come with preconceived notions, biases, and prejudice. That's just the reality. But it's the thinking, learned individual that will open his or her minds to the possibilities of what truth lies ahead. And when truth is found and discovered, the thinking person will modify their intuition, their ideas, their beliefs, so as to conform with the reality. Keeping an open mind is a powerful way to indeed make new discoveries. My fourth life lesson is to explore the consequences of new ideas. Every new idea should be a dawn, not a sunset. In the rest of the world, when people have new ideas, they celebrate. Oh, Bob had a new idea. Let's get the cake and balloons. Well, that's great. But the truth is, the creative mindset is one where when a new idea is presented, we say, that's a great new idea. It resolves the issue at hand. What else can we do with it? Can we take it further? Can we solve new issues with it? Can we understand other things better? That was our journey through mathematics, constantly taking one idea and applying it in some new direction. Number 5 is to seek the essential, to ignore all the superfluous noise around us, all that ambient nonsense, and figure out what is at the root of the issue and focus on that. Here, our issue was studying the numbers, and by doing so, and with laser focus, uncovered dramatic structure throughout all of numbers. Number 6 is to understand the issue. This seems almost trite because it's so obvious, but so often students will come into my office and say, Professor Berger, I can't do on the homework number 8. And I'll ask the student, well, what is number 8 asking? And the student will respond, no, I don't know how to do it. Not even realizing that the first, most foundational step is to understand what we're being asked to do. No one can answer a question that, in fact, we don't understand what the question's asking. So first, we must take the time to set a high bar for what understanding even means before we even tackle a particular issue. Then, we understand simple things deeply. This is my 7th life lesson. Well, we've seen this time and time again. We study very simple objects in our course, and slowly, through examples, we found proofs of very complicated theorems just by taking a look at an example, studying a simple illustration of it, and then all of a sudden, the more dramatic, more abstract theory blooms. Well, it turns out that in focusing on simple things, we actually realize that the simple is not so simple, but actually holds a plethora of complexity. And that actually makes the seemingly complex all of a sudden become tameable. Number 8 is to break a difficult problem into easier ones. We've seen this time and time again in our course with the divide and conquer approach that we've used and employed in a powerful way throughout. Number 9 is to examine issues from different points of view. Quite often, the vantage point upon which we take to look at issues will, in fact, influence us. Continued fractions allow us to see quadratics as a very, very nice type of object. Their expansions are periodic, whereas the decimal expansions reveal no particular structure. Number 10 is to look for patterns and similarities. Throughout life, we should always look at things closely. It's by looking closely at things and trying to genuinely, by intent, look for patterns and similarities. Even if we don't find them, we will see structure. The structure is there. All we have to do is see it. And we've seen that throughout our course. Well, I return to the parable of Thales. Mathematics and our understanding of numbers has expanded profoundly throughout human history because we were looking outward, pondering the mysteries of numbers that seemed, like the stars, all too distant to comprehend. Yet mathematicians and mathematics is also about looking closely at what lies at our feet. That is, at what lies close at hand and what seems common and ordinary. Great secrets and structures lie close by, to be uncovered only if we open our imagination to all possibilities. The limitless nature of numbers beautifully parallels the limitless nature of our own imagination. Using our creativity and imagination, we can conquer any challenge we elect to face. Looking at our world through the lens of number theory, we see everything with greater clarity and in vibrant colors, especially ourselves. It's been a great delight and a privilege to be able to share my world of number theory with you.